Okay, I'm going to claim that any vector v with components x and y, any column vector xy, is a linear combination of the two vectors v1 and v2, where v1 is 3, 1, and v2 is 2, negative 3. Okay, let's review quickly how we arrived at this question. We looked at linear combinations of v1 and v2, the two vectors v1 and v2 that we're talking about. We saw that the linear combination 2v1 plus 1 half v2 can be represented if v1 is the white vector here and v2 the white vector here. This combination, well, 2v1 can be represented by a vector along the line of v1, but of twice the length. And we've also seen that that vector, 2v1, is 2 times the vector 3, 1, which is 6, 2. A vector of twice the length of v1 in the direction of v1 has to be 6, 2. v1 takes us from 0 to 3, 1. Another v1 will take us 3 units this way and another 1 unit this way, getting us to the point 6, 2. There's your vector 2v1. Vector 1 half v2 will be just like the vector v2, but only half as long. So that vector, well, half of 2 negative 3 is 1 negative 3 halves. Now v2 goes over 2, down 3. Half of that should go over half of 2, which is 1, down half of 3, which is 3 halves. Okay. If I put this 2v1 head to tail with 1 half v2, I end up at the point 7, 1 half, the same as what I get from this calculation. Or if I put the vector 2v1 tail at the end of v1 and go over here, we can count spaces and see that we end up at 7, 1 half once more. Now, we looked to see if we could find graphically a representation of a linear combination of v1 and v2 that gives us a vector v. Now, we just drew a v1 and a v2, not very accurately. v2 is a little bit too long. And then we just, in green, we just slopped down a vector v. We said that, okay, if I want a linear combination of v1 and v2 that gives us v, first of all, we observe that positive multiples of v2 run from the origin to points of this half line, and negative multiples go in this direction, run from the origin to points of this line. Okay, all multiples have to lie along this line if they're rooted at the origin, so they have to be parallel to this line. If I do a line parallel to this one through the vector v, well, since this v2 is not parallel to v1, this line is going to intersect the line of v1 at some point, and where it does, I'm going to get a vector from the origin out to some point along v1 here. That vector is going to be some multiple of v1. We estimate that looks like maybe about 2/3 of v1. We've got a question mark there, and that's a question mark. Let's kind of put the dot under there to make sure we understand it's a question mark. Okay, and then we have a vector from here to here representing a multiple of v2. It would be a negative multiple of v2, and it looks to be about 2/3 as long as v2, so we conjecture this vector might be negative 2/3 v2. Okay, we observed that any vector, a vector from the origin out to this point, we can do the same thing we did here. We do a line parallel to the direction of v2, and we intersect that with a line through the origin parallel to v1, and we've got a vector from here to here. It's a multiple of v1, maybe 5v1, and a vector from here up to here, maybe negative 2v2. If we want to get down here, we do the same thing. We get to any point in the plane, and we say any vector in R2, therefore, appears to be a linear combination of v1 and v2. It seems totally obvious that should be the case just from the geometric interpretation. Now we want to go ahead and show that algebraically. Okay, so we're going to do some algebra. Okay, any v equal to xy is a linear combination of v1 equals 3, 1 and v2 equals 2, negative 3. Okay, well, a linear combination of v1 and v2 has the form C1 V1 plus C2 V2. For C1 and C2 could be any numbers. Okay? So let's let V equal to C1 V1 plus C2 V2 and see if we can use little algebra to determine what C1 and C2 are. Of course, we don't know what x and y are, but we're still going to see if we can solve this situation. And what we have to solve for is C1 and C2, because we're trying to find the multiples of V1 and V2 that give us this vector V. Well, we can write that equation now in terms of the column vectors. Okay, so this equation is the same as x, y equals C1 times V1, which is 3, 1, plus C2 times V2, that's 2, negative 3. And of course this equals well, C1 times 3, 1 is C1 times 3, that's just 3C1, and C1 times 1, which is just C1, and C2 times 2, negative 3 is similarly just 2C2, negative 3, C2. So, xy equals what? If we add these two, we get 3C1 plus 2C2, and C1 minus 3C2. So, three C1 plus 2C2 equals x. C1 minus 3C2 equals y, and we can solve by elimination. We could add negative 3 times the second equation to the first and eliminate C1. Of course, over here we'd have a negative 3y added to x, but we'd have x then minus 3y, and we'd have 12C2 equals x minus 3y and everything. We could write that out. Okay, it's easily done. And if we have numbers for x and y, then we can find the numbers. Okay, we're not going to do that. What I want to emphasize is that this situation gives us this set of simultaneous equations, but this set of simultaneous equations This is equivalent to a matrix product. It's equivalent to the matrix product okay, here it is. You can verify it. First row times the first column, times the only column here, is 3c1 plus 2c2. Well, that's exactly what we've got here, and that has to equal the number we have in the first row of this column, which is x. And 3 times c1, c2 is 1c1, which is just c1, minus 3c2, there we have it, and that has to equal y because it's the second row times this column, and y is in the second row. Okay? Now, there's a way of solving a matrix product of this nature, and we don't want to go there right now. But our conclusion is that to test whether an arbitrary vector xy is a linear combination of two given vectors, that can be written either as a set of simultaneous equations or as a matrix equation. A set of simultaneous equations can clearly be solved. You can write that set out, that system out, and solve it. You know, C1 will be some combination of x and y. I think I said it's x minus 3y all over 12. So x over 12 minus 1/4 of y. And then, you know, you can get C2, you can get C2 accordingly. Okay. We're not going to go into how you do the matrix product, except to say, just as kind of a preview, that this matrix product, now there's going to be a confusion on notation, so I'm not going to do that. Okay, so we're going to leave it at this. Again, very important to understand how this condition, the condition that this vector be a sum of multiples of two given vectors, can be written first in this manner. V equals some multiple of V1 plus some multiple of V2, where the multiples are C1 and C2. The multipliers are C1 and C2. This can be written ultimately as a system of simultaneous equations equivalent to a matrix equation.